You have a plug flow reactor, pure acetone, and 5 cubic meter of volume. How much of it can you crack acetone into ketene and methane? Today we are simulating a high temperature vapor phase plug flow reactor in Aspen Plus, and we are going to find out our exact conversion rate in just a few minutes. Let's jump right in. Hello everyone, welcome back to Chemical Engineering and Aspen channel. In our today's video, we will be simulating the plug flow reactor using Aspen Plus, and the engineering problem statement for today's activity is that pure acetone is fed into an adiabatic PFR, which is plug flow reactor, at a mass flow rate of 7.85 kg per hour. The inlet conditions of temperature and pressure of the feed stream are 760 degrees centigrade and 162 kilopascal respectively. In a vapor phase reaction, the acetone, whose formula is CH3COCH3, is cracked to ketene, which is formula is CH2CO, and methane CH4. The following reaction takes place: that the acetone, which is represented as A, is cracked to ketene, which is represented as B, and methane, which is represented as C. The reaction is in first order with respect to acetone, and the specific reaction rate constant expression is K, whose unit is per second, is equal to 8.2 into 10 raised to power 14 exponential of minus 2.845 into 10 raised to power 5 kilojoule per kmol divided by RT. This is the value of activation energy. This is the value of pre-exponential factor. The basis which is given to us is mass concentration, and our task is to calculate the conversion of acetone in this reactor while the reactor volume is 5 cubic meter. So using this statement, we will now go to the Aspen Plus and we will simulate the plug flow reactor to understand how we can simulate it and how we can provide our kinetics, and finally what is the conversion of acetone which we have achieved using this simulation. So coming here, we will first add the components acetone, ketene, methane, clicking on the next button, and we will select the property package as BWRS, which is Benedict Webb Rubin Stirling equation of state. Then we will click on the run button, and once the results are available, we will go to the simulation environment. So now we will select the required reactor, which is the R plug, and that R plug is rigorous plug flow reactor with rate controlled reactions based on known kinetics. So we will click on it, we will place it, then we will do the stream connections, feed required, and accordingly the product required up to 3, but obviously our system has one feed, control A, control B to adjust the connections. We will click on this S1, which is our feed, and that is at 760 degrees centigrade, 162 kilopascal. The mass flow rate is 7.85 kg per hour. The mass fraction of acetone is 1 while that of other is 0. If we do not specify it, it will remain 0. Then we'll click on this reactor. Since it is given in the problem statement that it is an adiabatic reactor, so we will click on this adiabatic reactor. No additional specifications required. Going to the configurations, it is a vapor phase reaction, so we will select process stream valid phase as vapor only, assuming that the diameter is 1 meter, and since we know the volume as 5 cubic meters, so we know the dia, so accordingly the length will be 6.366 meters. Then we will click on this reactions, we will click on this new, and we will add the reaction set as power law, and we will click on OK. Now we will specify the kinetics, but for this we have to first specify the stoichiometry. So click on this new, and the component for feed is, or for reactant is acetone, while for product it will be ketene and methane. Now the stoichiometric coefficient for acetone is 1. Since it is reactant, so it will be -1. For ketene and methane, it will be 1, 1. Obviously, we have to specify the exponent since it is given as the first order reaction. So for acetone, the exponent will be 1. And since it is irreversible reaction, so the exponent for ketene and methane will be 0. If it would have been the reversible, then we have some value of exponent over here. Click on this next. Then we will go to the kinetic. Reacting phase, it will be vapor. The value of pre-exponential factor is 8.2 E of 14. Then in activation energy, selecting the unit kilojoule per kmol, it is 284,500, and changing the concentration basis to mass concentration, or CI basis to mass concentration. Then we will click on this run button to see whether our column converges, reactor converges, and accordingly the reactor has converged. We will go to the stream results to see how much conversion of acetone is achieved in this reactor. So clicking on this mass flow, the inlet mass flow of acetone is 7.85 while that of outlet is 3.54. So if we click it, 7.85 minus 3.54085 divided by 7.85 into 100, it is 54.89% conversion of acetone that is achieved. If we talk about the molar basis, you can see that 0.135 moles of acetone are entered in the reactor, while at the exit of the reactor, 0.0609 moles of acetone, 0.074 moles of ketone and methane are produced. If we again calculate the conversion on the basis of the number of moles, 0.135158 minus 0.0609651 divided by 0.1351558. Accordingly, the conversion is same, 54.89% conversion is achieved in this reactor. If we go to the reactor results, we can see that the minimum reactor temperature is 421 degrees centigrade, while that of the maximum reactor temperature is 760 degrees centigrade. The residence time is 0.666 hours. So that was all about the process to how to simulate a reactor for the cracking example. And that is how you simulate an adiabatic PFR for acetone cracking in Aspen Plus. If this saved your hours of staring at simulation errors, drop a like, hit subscribe, and let me know in the comments what reactor or separation column you want me to simulate next. See you in the next video. Till then, it's goodbye. Thank you so much.